of the chapter. And what we're just, the beginning part is just putting everything together that we already know. Because, you know, we like to get things more complex, and so we're going to do complex lenses. So we're going to combine, we're going to put two lenses together, like they do with like binoculars or microscopes or telescopes. And so think two. All right? It's just that much better. Okay. All right. Or it's 2 times harder. I don't know. Okay, it is twice as much work, but it's okay. So here's the rules. We're going to find the image for the first lens. So you're going to treat it like 2 problems. You have a lens, and don't we know how to find where the image is of that?
Yes.
Okay. The image of the first lens, guess what?
That's the new
Is the object for the second lens.
Whoa.
Okay? The image of the second lens. Now, so this thing, right, creates this thing, and so this is the answer for the whole problem, because it was this and then to this. So it's not hard, but you have to be careful. Just that it's so easy to copy a wrong number. That's pretty much it. So be neat and tidy, okay? The magnification, the total magnification is the 2 magnifications multiplied by each other. Okay? That's it.
They're multiplicated.
Okay. Yes. They're. Yeah. What do we? How if you multiply multiples?
Multiplies.
So I don't know. Okay. All right. Let's do a problem.
Do we have to draw?
I am going to draw real basic lines. I'm going to draw. We're going to draw lines without numbers. Okay? So, what did I just do? Oh, I just pretended. Here. Here. F. There we go. Just put a dot.
That's an F.
Yeah, that'll work. Okay. So, parallel through focal point. Yeah?
Yeah.
And let's do the other easy one at this point, and that is, how about we just go through the center of the lens? Okay? All right. So here we would have, I just want you to realize that if we have light going through a converging lens, do you see it's going to turn out upside down like this if this guy is kind of farther out, okay? So we have this image that's upside down. Oh, sorry guys, yeah. Do you want? Anyone need? All right. So let's look real quick what happens next. We're not used to starting with something upside down, are we? So if this is upside down, what do we do? Same thing.
What?
But where's your second F?
Yeah, I don't know. Let's just, again, just draw a dot.
That's reassuring.
I know. Here, let's just do that. Just make it about the same. So let's assume, oh, that's my example. We have 2, they are the same focal length. So make it about the same dot out. That's not very good. Let me make it about the same. So, ding, ding. Okay, wherever you put it.
That was so accurate.
I know. Okay, so now we have this guy. So again, parallel. Oh, that's not even parallel.
Oh, I did it the other way.
This is kind of fun.
Okay.
She writes me a vectors.
I can't make Maddie uncheery about this chapter, no
Wait.
matter what I do. So this is.
I haven't started
That's not true. You can give her like a C on the test.
She's not going to get a C on this test.
I get a C on this test.
There is no way.
Then I've given up on life.
I would agree. Okay.
Are these lines not in the middle of the lens? Is that just me? I don't know. It looks like it's below, like down.
Just
Go
this
with
is
it,
a.
Lou.
There's not even numbers in this picture. We're just kind of drawing this. Okay. So where do we get now? So we can see the biggest thing that we can see here. Oh Lord.
It's upward.
Is that we've made, so what's one advantage of having two lenses?
You don't have
What's one reason you might want to have two
You don't have to
lenses?
flip it.
Is that when you look through it, the object's not upside down.
Oh, yeah.
Wouldn't that be good when you look through binoculars?
Look at that.
Yeah?
Yeah.
Okay,
Oh,
all right,
that's great.
okay. All right, let's just do some math. So, and I have it laid out nice. So I'm gonna write first to number one. I'm gonna deal with this first lens here. And I'm gonna do 1 over di plus 1 over do equals 1 over f. And I always write it out because I'll screw it up. I wanna know where the image is. Whoops. But I know the object is where? I said, first of all, these are 60 centimeters, so I'm going to put 0.60. My focal length is 0.20. All right? And so if I do this, 1 over di equals 5, right? This is 1 divided by 0.2 is 5. And then I'm going to bring this over and subtract, minus 1.667. And so after I do that and flip, I get a positive 0.30. Okay? Now, remember what these things tell us. So 30 centimeters from the lens, and the positive tells me what?
Opposite of the object.
Okay, it's on the other side of lens, right?
Yeah. I learned that.
The positive is where we normally expect it to be. So a converging lens, it's here. This would give you is a negative distance. This is a positive distance. Now, tricky. Is this, now I'm going to do, wait. Let me first, before I forget, let me find the magnification of the first lens. So negative di over do, and I get negative 0.30. No, wait, yeah, negative of a positive 0.30 over 0.60. And so I get a magnification, right, of negative 0.5 times. Why is it negative?
Inverted.
Okay, inverted. Good job. And it is diminished. Okay, I can't even spell that. Whatever. Okay. I'm going to now run this all again. 1 over di plus 1 over do equals 1 over f. My f is the same, 0.20. I'm looking for di of the second lens and of the whole thing. What do I plug in for my distance of my object? Everyone stop and think.
Like from a number there?
I need a number, yep. Oh,
Is it just 0.3?
is it, the way I'm stating it, is it just 0.3?
Maybe not.
Probably not. Can we, look where this is.
80 minus.
So you see this is where, this is now going to be our object. And I need to know the object distance
Oh, to that point.
to that lens.
That's a quite easy.
Does everyone see that we can't just transfer that? That's the only tricky stuff about this. It's not hard. You just got to stay on top of it. So we know this was 0.3. Well, this is 0.80. So before you do anything, right, your D20, right, is 0.80 minus 0.30 equals 0.50. Okay. Yes?
Yes.
Yay.
That's it. So now it's just plug and chug on that. And I'm just going to say DI2 is 0.333. Hey, there's my answer. What is the position of the final image? 33 centimeters, and it's positive to the right side of that, right? We just discovered this. Whoops, two, whatever. Okay, what is the overall magnification? I still need to do magnification of the second one. So, negative 0.333, right? Yes. Okay, but you're not gonna like this.
0.5.
Okay. Yeah. Yeah, so this one as well, it's gonna be negative 0.667, okay? Now, what people aren't gonna like is you look at this, Miss Jones, it's negative, but it's upright. So you lied, but it started upside down, so this negative just is telling you it flipped.
I mean, it
See, 'cause
inverted
this-
from the inverted
It
position.
inverted, so it's not, it's still yeah, let me just say that. It's still inverted. The image is inverted of your object, but it's just not upside down.
So to get the total
M total equals that one, our negative 0.667 times our negative 0.50, and miracle of miracles, yeah, oh, yeah, we're back to 0.33.
Oh yeah, that makes sense.
And yay, what do we see?
It's
Overall, right, our object is upright, right?
this
And
one-
diminished.
Is the overall magnification always going to be equal to the DI2?
Oh.
No, that's my this going to sleep.
Okay.
It'll come back.
I'm too tired.
It's still annoying.
Like set it so it never goes to sleep.
No.
No, I think it's just stupid numbers.
Okay.
Okay. All right. Okay, that was fun. That wasn't too bad.
But then you get cut
So,
caves.
well, let's look at this interesting scenario that you can apply.
Okay. That'd be interesting.
Yeah. So, let's say you wanted to know the focal length of an unknown lens. Okay, you know we just did that lab, and you had a converging lens, and you could put the little piece of paper, and we got the candle glowing, and you could see it and go, woo, 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 and find out the focal length, right? Yeah? Okay. Well, why didn't I have you do that with the diverging lens? Can you move, could you have gone on the ruler and moved the diverging lens in and out till you, so, so you experimentally, you could not do that lab with this, but you can do a trick.
You can have
Because
it.
you can make a couplet, you can add this to this, and then it would. Because this will make this converge. And this one's rays converge here. And then this lens would make an image here. So this is the image, the final image, where this lens took these rays, image, and made this. And so we can get a real image out of the diverging lens that you can measure. All right? Okay. Crazy stuff. Okay. So we can get where an image is seen, and so what we have to do it with, though, is distant light. So if we have parallel light, this is what makes this easier to do math on. If you use far away or parallel light coming into the lens, we automatically know the answer for this first one and don't have to do any math for it. Tell me where the where the image is going to be of this one if it's from parallel rays.
The focal point.
The focal point.
Oh, right.
So we right away know that whatever the focal length of this lens, we know that is where the the DO is for this lens.
Oh, okay.
So we just simplified this whole process. Okay? All right. So we also know if we experimentally measure and see something right here, then we know that's for the combination of the two. Whatever you saw, right, is both. Okay? So we know that. Okay? What else did I want to say? That's pretty much it. So let's try the math on it. So since light was so we already said that. So since light was from a distant source, the first lens image, its focal point, becomes the object for the second lens. And so what number am I going to call that? So what is my distance of object for the second lens? Careful. If you read that problem, did you see that that converging lens had a focal length of 16 centimeters? What am I going to call DO in that picture? So I know it's not up right now because I have this. Isn't it right there? So isn't my object here? It's not 16 because 16 would imply it was on this side. So, okay? All right. Now we're home free. 1 over DO. Which one is? Oh, I did DI. Why did I? 1 over DO, 1 over F. So I know the image, because that was measured, is our, you know what? I think I even just left it in these units. Doesn't matter, because I'll just get a focal length in centimeters. And this is negative 16. And I can figure out what the focal length of that lens is now with just math. And so if you do this, you get a negative 36.5 centimeters. Now what's even cool, tell me about that negative in this case. What does that mean? The negative focal length.
It's up.
Virtual?
Not the focal length. The focal length, remember, tells you really about the bend of the lens. We gave a negative focal length in 2 cases. One was a convex mirror, and the other is a diverging lens. So it's just a diverging lens, right? Has a negative focal length. Do you remember we used the other F to do all the lines, right? It's from the other side, okay? All right, so do you see how this became super simple math by making light from a distant light source? And so if you just measured that combo's focal, or where the focus was of the image, you can find the focal length of that lens. All right? So, kind of cool. All right. If you have 2 lenses in contact like this, it turns out, I gotta say, it only works, that only works if the focal length of the converging is less than the focal length of the diverging. Otherwise, it will put the image in the wrong place and you can't get an image. Okay? All right. All right. Overall result for lenses that are in contact, the equivalent focal length ends up being 1 over F, if you know the focal length of the other, plus 1 over the other focal length of the other. And you can keep doing this. If you have multiple lenses, you could keep adding, then 1 over F3, etc. Okay? So the equivalent focal length is a sum of the reciprocals of their focal length. All right? So that's a nice handy dandy thing. Okay, last equation called the lens maker's equation, because this is what I was mentioning the other day. If you have a strong prescription, you might want your glasses, which are not glass, right, to be made out of another material, right? Glass, a certain kind of plastic, another kind of plastic, polymer, and which all have different indexes of refraction. Because if you have a different index of refraction, you don't have to have the same curvature, as much of a sharp curve, and it might and it doesn't have to be as fat then, because it doesn't have to curve as much. And so this equation relates the focal length of the lens. And do you realize that 1 over f, what's 1 over f better known as?
Diopter.
The diopters or power in diopters. So the diopters or power of the lens is related to how big of an N you have. Now remember, N was how much a material slowed light down. So, you know, where diamond was the highest number, all right, and then air was the lowest number, all right. And so that's why this is air right here. It's comparing it to air here. And so the bigger this number, right, the higher power lens you can get for a given curve. Okay? All right. Okay, what else did I want to say there? Okay, I wanted to say that. Okay, so what can we do? So we can take a lens and make it different on both sides. That's why there's an R1 and an R2. So we're used to only having what's called a doublet, where this side and this side is the same. But we can do, look at, do you like these names? We can have a plano-convex. Plano meaning one side's flat, okay? A convex meniscus or a concave meniscus, all right? Or yeah, we're having lots of fun here. And here, let me explain this. So let's look at this one. What's the difference between this and this guy? Do you see that this one, if you look at it, this, tell me the R of this compared to the R of this. This R, that, which one would be a bigger circle?
Oh, the one on the inside.
Okay, let me just help you with that.
Oh, I thought we were comparing.
We're comparing the radius of curvature.
I thought you were comparing.
And do you see that this one, do you see what I'm saying?
Yeah. That makes
Did
sense.
you get with that?
Yeah.
Now look at the formula, okay? And so let's look at what happens. So if this R, okay, I have to think hard out. If this R is smaller, right? If this R is smaller, then this part is bigger, right? And you're going to get a positive focal length. So it's going to end up being converging. All right? Make sure. Yes. And if you get the opposite happening, that's what this one is. Do you see this one is sharper? Then this number is going to be bigger, and hold on. Yeah. Oh, R is smaller. Yeah. This is smaller, but this ends up being bigger. And then hold on. Oh. So it ends up being diverging because they're because of the difference between those two. Okay? And you're playing this game with the bigger and smaller thing. All right? Okay, we're going to do a problem. We're going to see. Oh, how about this? This is, so a convex surface, R is positive. A concave surface, right, is negative. Oh, that's the big deal, because this is then considered, do you see that that's the back side? So that looks like a diverging lens, while this, with the front side, with the light hitting, is going to be a convex. So we have convex versus concave on the other side, which will make you a bit crazy. If it's a flat surface...
But isn't the one above it like the same kind of concept, though?
Yes. So again, but it'll keep, because this one is a smaller curve, this is max, this will end up minus, this will end up being positive.
So it's
But
just
this one,
the outside
because the other one, it's negative, it's going to make the whole answer become negative. All right? If it's a flat, what does light do when it's flat? Nothing. So R ends up being infinity, and it doesn't even act like a lens. Right? It doesn't affect your answer. Okay? All right. So F is negative, like usual. If you get F being negative, it's going to end up being a diverging combination. So these combinations are diverging, and these combinations end up being converging. Okay? All right. Okay. You can rotate the lens in the long run. When you plug in for the form, it depends on how you look at it, and it should all work out. All right. So if you take a lens and look at it from either direction, you're going to get the same kind of image coming out of it. All right. Let's just try a problem. Oh, I got to scroll this up. Okay. We have a convex meniscus lens, n equals 1.55, radius of curvature of 22.4 on one side and 46 on the other. So if we draw this, right, the 22 is bigger. No, 22 is smaller, so that's going to be a tighter curve, and this is going to be a more gentle curve. All right? This is my F of 22.4, and this is my F of my 46.2. Okay? So you're going to have this kind of a lens. All right. So what if light's coming in like this? This surface is convex. When light leaves, does whatever through here and leaves, this surface, right, is going to be concave. Yeah? Okay. Am I hurting your head? All right. 1 over F equals, then our N is 1.55. All right, minus 1, which is just air. And then we're going to do 1 over our 22.4. All right? Right, plus a negative 46.2. All right? Because this is acting like a diverging on the backside. All right? And we can see, well, we're going to see. So if I don't have an answer. Uh-oh.
We don't really need one.
All right. 1 divided by 22.4. Okay. Do I need this? Hold on. First of all, I should make this in meters. Let me just do meters. Just to make sure. Okay. 1 divided by 0.224. 4.46. 1 divided by 0.462. 2.16. I can do this in my head. All right, so I got this one minus 4.46. All right, and so I have a negative 2.295 times 0.55. Did I do that? No, I didn't say that. Okay, sorry. I entered because the last number was in my calculator. I was bad. Okay, so then we times it by 0.55. And then take the reciprocal. Do I have a 1 over x? No. Okay.
0.79.
Yeah. So the overall focal length, right, is, did I do something wrong? Okay.
So like, I'm confused. How would it work for concave meniscus?
So the other one,
Yeah.
so
Like,
the
what's
difference is that you're gonna plug everything in the same, but the concave, this is smaller than this one, so this will become negative.
But like the signs are still the same.
Yes, but this will override this one. And so you're gonna get a negative overall F, so it's gonna be overall divergent.
Okay.
You got it?
Yeah.
Okay. Alrighty. So now you've got that pretty worksheet with pictures on it. So with that worksheet, the only thing to be careful about is that your image from the first, don't forget to convert it on like there's a little meter stick underneath it. you need to put it in the right place compared to the second lens. And that's really the only thing that I feel you can do wrong.
How do you want us to draw on a black box?
You don't have to draw at all, it's all math.
Okay, why?
I'm sorry.
That's okay.
I'm sorry, Maddie, it's all math.